Hello once again, calculus type people. How is everybody doing today? Hope you're having an amazing Friday or Saturday or Sunday, whenever it is you happen to be watching this. Okay, let's jump right in. Intermediate value theorem. This guy is going to be extremely important to you no matter how high you want to go up in mathematics. You can go to the highest math class you could possibly take. They're probably going to involve something with the intermediate value theorem just because it's a very straightforward theorem. All right? If f of x is continuous, everybody remember continuous, I want you to write down that there are three reqs, REQs, three requirements for continuous. Remember we talked about that a little while ago. I'm going to go over it again in a second. On a closed interval AB, these are your x values from A to B, and k is a number between f of A and f of B. So k is a number between f of A and f of B. That means that k is a y value. Then there is at least one number c in AB. C is an x value here. There's at least one x in this interval such that f of c is k. Basically, here's what it's saying. This guy is A, right? This guy's x value is B. If f of x is continuous, like this function is, no holes, no gaps, no breaks, on a closed interval from A to B, these x values here, and k is between f of A and f of B. Here's f of A. Here's f of b. K is a y value anywhere between one of those. Then there is at least one number c, which will be the x values for these points, that we can plug in to f and get k. Basically, here's what it's saying. Here's a point, here's a point. If the function's continuous, it's going to go through somewhere in the middle. Make sense? That's like saying you have to go through the equator to get to Antarctica from here. To go from here to Antarctica at some time, you are going to have to cross the equator. It's basically what it's saying. All right. If f of x is continuous, this is another portion of this, on the closed interval AB, and between A and B, f of A and f of B, there's a sign change, then a root exists. Basically, again, if you are up here in North America and you go down here into, Antarctica, at some point you have to go through the equator, the x-axis. So if f of A is positive and f of B is negative, you have to go through the x-axis. Or vice versa. If f of A is negative down here and f of B is positive up here, at some point you had to cross the x-axis if it's continuous, right? So there's one thing I want you to write on the very top. I want you to put quotation marks. Prove that, let me get my hand out of there. Prove that a value exists. Prove that a value exists. If you ever see that on the AP Calculus test, that means they want you to use the intermediate value theorem. I can't say it any more bluntly than that. Prove that a value exists means use the intermediate value theorem. Okay? Let's jump into it, see what happens when we do this. Example 1. Given the graph of f of x over the interval -1 to 2, here's the graph of f of x. Before I even get into A and B and C and all that jazz, let's just look at this graph for a minute. It's linear. We've got a point from -1 to -2, -1 comma -2 rather, and 2 comma 5 up here. So if you count your slope off, it's up 7 over 3. You got a slope of 7 over 3. Very quickly, I can come up with an equation for this graph. using y minus y1 equals m times x minus x1. That's point slope form, right? You got a point x and y, plug them into here, and you get your you got your slope, plug it into m, and you get a equation for a line like y plus 2 is equal to 7 over 3 times x plus 1. Right? Setting this thing up, a couple things that we need to discuss here. When you're going through and making an equation for a line in calculus, we can stop right there. I don't have to get it to slope-intercept form. What I would recommend doing is go ahead and bringing that 2 over so that you have y is equal to 7/3 x plus 1 minus 2. Remember that these are supposed to be y minus y1, x minus x1, but since they're negatives, I'm going to throw both of those into positive, subtracting negative numbers here. I've actually done this video once before and I skipped a negative. No! If I was just teaching, that wouldn't have been an issue. I just erased it and started over, but I didn't want to mess anybody up. So I can leave it like this. You don't have to distribute. There's no need to distribute. Don't worry about it. All right? Okay, so A says to determine if it's continuous over an interval. Remember, 3 things have to happen. First, f of c has got to be continuous, whatever the value for c is, right? It's got to be continuous. In other words, can I pick any x value in here and have it be continuous? Yes, there's no holes, there's no asymptotes, there's no breaks, none of that. So we can state, just by looking at the graph, that f of c exists. It does exist. I can pick any x I want and I can find a y that's inside of that interval. Next, the limit has to exist. There are no holes, there are no asymptotes. So yeah, there's going to be a limit there. So we'll say the limit as x approaches c of f of x exists. So remember, you have to state that the function exists, you have to state that the limit exists, and then you have to state that these two things are equal. The only time they wouldn't be equal is if there was a break in the graph, a hole in the graph, a removable discontinuity in the graph where there's a hole with a dot above it. There's none of that there, so I can state with assurance that f of c is equal to the limit as x goes to c of f of x. And because of all of this, therefore, it's continuous for all x, and we can say in -1 to 2. Because all those 3 things are good and valid, I can say with a surety that it is continuous, because I have proven all 3 of those things. B says determine if a root exists over the interval. Well, if you look at these 2 points, like we'll use -1 first, f of -1, the x value of -1 gave you a y value of -2 right here. F of 2 gave you 5. And if you notice, between these 2 numbers, there is a sign change. Your little therefore dots. Therefore, a root exists. Remember, if there's a sign change, that's what it says right below the graph up there at the top, then the root exists. Finally, C. They want to find a value for c such that f of c is 3. This is why we needed the equation, such that f of c is 3 over the interval -1 to 2. So they want me to basically find the x value that gives me a 3 for y. 7/3 x plus 1 minus 2 is equal to 3. You are setting f of x.
Teachers, would you please do an ID check in your classrooms at
Wow.
this time? They should only have IDs from this year.
So Miss June is, or
Make
Miss
sure that
James
this
is on
year
our
ID, have them
video
take
now.
the
I'll
other
have to send
and
this
put
to
it
her.
away. Students, if we see another year's ID, we will take them and cut them up. It's illegal to wear two IDs. Make sure you have your ID and your ID from this year.
Thank you. Okay, so solve for x, multiply by 3 over 7, multiply by 3 over 7. X plus 1 is equal to, it's 15 over 7. Subtract 1, so subtract 7 over 7. Common denominators, please remember that. And you get what, 8 over 7? Which, if you look at your graph, that's a little bit more than 1, right? This is the C value that it's looking for. And if you look at your graph, where y is 3 right here, that's x value is just a little bit more than 1. Make sense? So prove it's continuous, 3 things. Prove there's a root, we're looking for a sign change, and then find out what x value gives you that y value. Okay? And then you have to verify, obviously, is this in the interval -1 to 2? Well, yeah, of course it is. Let's go to the back. Functions can be continuous on closed intervals or in their domains. They don't have to be continuous over the entire thing, just on the interval we pick. For example, this guy right here. This is a semicircle with a radius of 2. So basically it looks like this. 1, 2, 1, 2, 1, 2. And right? -2, 2, 2. So it's a semicircle. This semicircle is continuous over the interval -2 to 2, which also happens to be its domain, right? So for each of the following problems, tell me if it's continuous over the interval, tell me if a root exists in the interval, and then find a value f of c equals k over the interval. So for number 2, the example here, here's my interval, here's my f of c, right? This is my k, they want me to find out what c is. So first, do a little I, because that's what we have is i's, I, and I. Tell me if it's continuous. For this function, is there anything I can put in for x to make this not continuous? No. So, is there any x I can put in to make it undefined? No. Therefore, f of c is going to exist. Can you take the limit of this function anywhere? Yeah, because there's never a point where you'll have an asymptote. No asymptotes to be found here. So the limit, as x goes to c, of f of x also exists. Because there's no possibility for anything to go wrong. There's no divisions, there's no square roots, none of that. No piecewises. Alright, so because of that, you can say that f of c is going to equal the limit, as x goes to c, of f of x. And I'm going to have to stop there. It's getting very close to, well, let me keep going. I got about a minute left. It's getting close to my limit, though, so I may have to stop here in just a second. So let's go ahead and finish this up. Therefore, it's continuous over 1, 2. It is continuous over that interval, right? All right, I'm going to stop here. I got about 30 seconds left, so we're going to have to pick this up in part B. Look for part B, por favor.